Hi everyone, my name is Mark Guzman, and today I'm happy to present my joint work with Jikung Feng and Jim Dai. It is called Scalable Deep Reinforcement Learning for Ride-Hailing. So today, ride-hailing apps are super popular, and three major companies, Lyft, Uber, and Didi, together serve more than 50 million passengers per day. And one of the important goals for these companies at this point is to make sure that they can provide a reliable, trustworthy means of transportation, meaning that they want to make sure that they are able to fulfill most, if not every, passenger's request. So given this goal, in our work, we focus on optimizing ride-hailing service control policy to maximize the matching rate between passengers and drivers. So let me start with a description of the ride-hailing transportation model that we'll consider. So first, we assume that a service territory is divided into R regions. The service network consists of N cars or drivers that are distributed across the service territory. We assume that the number of cars is fixed. We assume that each working day starts at the same time and lasts for 8 minutes. We also assume that the number of new passengers that arrive at region O at this minute is this number follows a Poisson distribution that depends on the region and the time of the day. So the number of new passengers is a random variable that is time dependent. So we assume that if a driver wants to drive from region O to region D, then this probability is equal to POD. That also depends on the time of the day. So once a passenger arrives to region O, with probability P that depends on origin region, destination region, and time of the day, it wants to drive to region D. So duration of each trip is deterministic and equals to tau ODT. This assumption is not essential, and basically our method that I will discuss later can be applied for the models with stochastic duration. We assume that each passenger has a deterministic patience time that equals to L minutes. That means that if the system cannot provide a driver who will pick up this passenger within L minutes, then the passenger will just leave the system. So we assume that if the system assigns a car to fulfill a passenger's request, then both the passenger and the driver have to accept this matching. So we assume that the ride-hailing service system has a centralized planner. So that centralized planner is a person or automated system that in real time receives ride requests and also observes locations of cars and the activity. So based on this information, the centralized planner assigns tasks to the drivers. And there are three types of tasks that can be assigned. First is car passenger matching. So the driver is asked to pick up a passenger and go to the destination according to passenger's request. Second type of task is empty car routing. So meaning that the centralized planner can ask a driver to relocate to another region without any passenger. And finally, the centralized planner can ask a driver to stay at its current location, idling without picking any passenger or driving to another location. So of course, we want to optimize how the centralized planner assigns different tasks. So our goal to find a control policy that will maximize the total number of car passenger matchings during one working day by the entire ride-hailing service system. So this control problem can be formulated as a finite horizon, discrete time, undiscounted Markov decision process problem. Of course, we know that we can apply dynamic programming methods to solve like any MDP problem. However, in our case, there are two challenges. Challenge number one, the centralized planner doesn't know traffic parameters, meaning that the model is unknown for the centralized planner. Challenge number two is a large action space. So let me give you more details why we have a large action space. So basically, at each decision epoch, the centralized planner, first of all, should address all available cars. And second thing that the number of there is a set of passengers with different ride requests. So the combinations how cars, so there are many combinations how cars and passengers can be matched. Moreover, as I said, the centralized planner can ask a car to relocate to another location without a passenger, or to stay at its current location. So the number of combinations becomes even larger. So as a result, the centralized planner, each decision epoch, the centralized planner chooses amount more than 3 to the power of IT actions, whereas IT is the number of available cars at decision epoch T. So the number of actions grows exponentially with the number of cars available in the system. So now let me explain how we are going to overcome these two challenges. So as I said, challenge number one is that we don't know the model. So we will use the reinforcement learning framework, meaning that even though the underlying dynamics is unknown, we still can try to find optimal actions by observing the sequence of data. So we will use the proximal policy optimization deep reinforcement learning algorithm to find, to optimize and learn optimal control policy. So challenge number two, it's a huge action space, and this challenge will be overcome by introducing sequential decision-making process. So let's assume, so at time t, at decision epoch t, let's consider action AT. So this action can be represented as a set of atomic actions, where each atomic action encodes a task for just one of the available cars. So so our idea is we can sequentially generate atomic actions, so tasks for available cars, until each available car is addressed. So let me explain it in more details. So let's say our current system state is equal to as Ti. So this is the system state at decision epoch T after atomic actions have been already generated. So we have our policy pi that that returns atomic action given our current system state, and this atomic action is generated and is equal to the as a pair of two regions, origin region and destination region, and that's all. So in total, we have r to the power of 2 atomic actions. So we have different like r squared combination of like 2 regions. Okay, so let's say our the centralized planner generated, or our control policy generated this atomic action, like OD. What should we do? What should we do with this atomic action plan? Meaning that what driver should be assigned to this action and what this driver should do. So in short, basically, like in region O, we just pick an arbitrary driver to fulfill this task. Of course, the real ride-hailing application, like ride-hailing app, can additionally optimize this choice, but we just pick an arbitrary driver at this location, at location O. Then, if there is a passenger that wants to drive from O to D, so which trip coincides with our atomic action, then we do passenger car matching. If there is no such a passenger, then 2 actions or 2 possible tasks are left. So if O is equal to D, then the centralized planner asks a car to stay at its current location and do nothing. If this is origin and destination regions are different, then the car will relocate to region D without any passenger. So as a result, like we basically generate atomic action, then assign, then find some driver to assign a task, and doing this sequentially, we basically find a batch action that we will use for at this decision epoch. So as I said, we use proximal policy optimization algorithm to optimize control policies. So let's assume that our current policy is PAC-C, where C is a set of parameters. So we use the parameterized family of policies. And we want to find a new set of parameters, theta, so that pi theta outperforms policy by C. So we run the system for k working days using our current policy by C. We observe the data, and then based on this data, we construct the PPO loss function and optimize this with respect to parameters theta and find a new control policy by theta. So we applied our proximal policy optimization algorithm for the n-region transportation network that we borrowed from Broman et al. Paper. So this network was designed based on the real data that was released by ThA company. So we also compared the performance of our like PPO policies, or the policies that the PPO algorithm outputted with time-dependent overhead policy, which also was proposed by Broman's et al. Paper. So what we can see that our the final policy that was produced by PPO algorithm could find like a driver for more than 85% of passengers. Moreover, it outperformed the time-dependent overhead policy. And why we believe that this is means that we have successfully applied like PPO algorithm is because the time-dependent overhead policy requires model knowledge. At the same time, the PPO algorithm doesn't require it, and still it outperforms the time-dependent overhead policy. So as a result, we proposed a method to find like optimal control in like quite complex ride-hailing transportation model. If you want to know more details, please check our paper. And thank you for your attention.